Subject Zero here. Recently, the good folks at MIT developed a way to make graphene that is fast, cheap, and scalable. But how does this method work? Here at Subject Zero Labs, we just don't talk about science, we show it to you. And we were able to acquire one of these machines to show you firsthand how it works. Not that we really have one, but we do have animations which will hope you like it and maybe gives a thumbs up. Nevertheless, before we start, let's talk a little bit about where this technology comes from. One of the things that we know about diamonds, nanotubes, and graphene is that it's much easier to grow them from what we call a seed. Like if you already have one diamond or a nanotube, you can easily grow it by bombarding with chemicals at high pressures and heat. So what they did was they got this seed, which is nothing more than a tiny piece from an actual diamond, and then they'd apply heat and pressure along with what they call chemical vapor deposit, which are carbon molecules like methane that is sprayed onto the seed. After some time, you will have a grown diamond, more like a few days. Also, in this process, after a while, the diamond starts to lose its shape, or the edges get burned if you think about it, and therefore it cannot be continuous, again limiting the product to small pieces. So in terms of diamond making, you would usually get for every less than 1 millimeter thick seed about a 1 centimeter cube. The same principle is applied for nanotubes and graphene, however this was limited to very small sizes, so if you would like to get enough graphene, for instance, to actually make something useful out of it, you would be limited to tiny amounts of maybe a few centimeters, and then again all the other processes that exist are too costly and still don't produce as much as we need. So think about this, you have these huge machines that take a lot of space and only spit out a tiny fragment of what you need. Building anything out of that will take centuries. And then on top of that, to make the purest product possible, vacuum chambers are necessary, and that makes the whole thing way more challenging. The way to go would be just to work inside these chambers with some kind of mechanism to remove whatever was already created and leave space for a new sheet to be formed. Hence the roll-to-roll method that MIT developed. Ladies and gentlemen, I give to you the MIT roll-to-roll graphene chemical vapor deposit. Let's take a look at the machine. As you can see, we have two chambers that are connected by a pipe. Basically, these two chambers are called input and output. The input chamber is where we have the beginning of the pure copper roll along with the gaseous exhaust that pumps the gas into the chamber. The idea is to have the sheet roll from one side to the other while gas exhaust pumps in methane on top of the copper plate while heat is also applied. This is what's called the CVD or chemical vapor deposit. Think of it as a molecular 3D printer, because usually they already have a seed available in the roll. By spraying the chemical onto the sheet, the molecules will self-arrange and continue to create more graphene, growing what was already there in a slow reaction. Depending on how you start this process, the seed here is not really necessary because the copper has some properties that facilitates the formation of graphene. However, the presence of a seed would make things much easier. There are more technical parts to this, like optimum temperature, amount of chemicals being sprayed onto the sheet, rolling speed, distance from the roller, and so on. To keep things simple, you need an optimum temperature to make the reaction happen at a constant rate. Too hot, and the vapor molecules will not go onto the sheet, and too cold, they won't bind properly, creating impurities in the sheet. Also, the methane gas has to be at the highest purity, or else you will get gaps that may disrupt the natural pattern of the hexagonal shape of the graphene. Next is the rolling speed. Again, too fast and the vapor won't bind, too slow and it will create undesired layers. And lastly, we have the distance. This is important because you need to keep the temperature at a certain level that won't change the process while increasing the length. So this would be the challenge of scaling production. But why is this achievement so important? Because this material has the promise to cover the last remaining problem of energy storage and rechargeability. It is known for some time now that graphene has the ability to store large amounts of energy in small batteries while being able to recharge in seconds, which would be the perfect battery. Moreover, it also can help current lithium-ion batteries to charge faster because of its high conductivity. We're talking about solving a lot of problems of energy needs for society society and also space travel. Like for instance, it is speculated that a battery of the size of an iPhone will have enough energy to replace all the batteries currently on a Tesla, which is about 7 to 8,000, and still give more kilometers per charge too. Sounds like science fiction, I know, but cool nevertheless. And of course, if batteries get to this level of efficiency, then that means a lot for the solar panel industry also. Now, if all of this comes true or not, don't look at me, I'm just a messenger. I've been following this tech for a while now and actually expect a lot out of it. So I guess I'm hyped as much as everybody here. So if it actually fulfills its promise, what does that mean for space travel? Aside from the energy storing capabilities, in about a decade or so, we will also be able to make ships that can withstand anything that space has to offer. For instance, one of the main issues that the ships have to go through is re-entry heat deterioration, which happens every time they enter a planet's atmosphere. However, with graphene-based structures, they would be a thing of the past because it can stand much more heat than any other material, and it would be the cheapest to produce by far. It is also very light and really strong, which reflects on the amount of load that can be brought up to space. Basically, all the weight that you save from the ship itself can be translated into the load amount. Yes, there are a lot of promises coming out of this technology, but we don't have time to talk about all of them today, so I guess we'll have to do this in another video. Alright folks, that's it, we're done here.